Okay, so we're going to have a look at another question here. This comes from a uni Calc 1 paper from 2014. This is a little bit more complicated of a question. This has a bit of working associated with it. You really have to know how to use the vector mathematics you've been taught. So this is question 14. We're told the planes, so plane 1 is x plus 3y plus 4z equals 5, and the second plane is 4x minus y plus 3z is equal to minus 1. So these two planes, we have to work out if they're parallel, or if they intersect at one of the three listed lines, or if they actually don't intersect at any of those lines, but they intersect at some other line. So the easiest way to do this is we're just going to find the line of intersection. And I will note, just from looking at this, it's immediately obvious that the answer is E, because E has the correction in it. That was the answer. It had a typo in it. So the E is none of the above. In this case, obviously, that's going to be the answer. But the important thing here is how we calculate this, right? We need to find, are these parallel? We need to check that. Then we need to find what the equation for the line of intersection is if they're not parallel, and then go from there. So the way we're going to do this is we're going to look at the normals. The normal for plane 1 is 1, 3, 4, and the normal for plane 2 is 4, minus 1, 3. Now if these normals are the same or are sort of scalar multiples of one another, then these two planes will either be parallel or will be the same plane. These normals are not the same, nor are they scalar multiples of one another, so therefore not parallel. Right? A is not possible in this case. So given that the two planes are not parallel, they must intersect somewhere. Where they intersect, they will form a line. Right? The intersection of two planes always forms a line unless the planes intersect completely. They are the same plane, in which case the intersection is not a line, it's actually a plane. It is that plane, right? Two planes that overlap each other completely. The intersection is the entire plane. So now we need to find the line. The way we're going to do this is we are going to solve these equations simultaneously. We're going to use elimination method to cancel some variables so that we can get some equations with only 2 unknowns in them as opposed to 3. So let's have a look here. If we multiply this first equation by 4, we get 4x plus 12y plus 16z equals 20. If we multiply the second equation by 3, we get 12x minus 3y plus 9z is equal to minus 3. Now if we subtract these two equations, we will get our first new equation, which we'll call 3. So 4x minus 4x is 0x. 12y minus minus y is plus 13y. 16z minus 3z is plus 13z. This is equal to 20 minus minus 1. That's 21. So here we're going to have, if we rearrange this for y is equal to 21 over 13 minus z. So this is our first equation, which is not a function of x. So this is only of 2 variables. Now we're going to do the same thing, but this time we're going to try and eliminate y. Here we eliminated x, now we want to eliminate y. So the way we're going to do that is we are going to subtract one of these equations from the other equation. So another new equation, equation 4, we're going to add these actually, because we have 3y here minus 3y here. Add these, the y's will cancel. X plus 12x is 13x. 3y plus minus 3y is plus 0y. 4z plus 9z is plus 13z. This is equal to 5 plus minus 3, which is 2. If we rearrange this for x, this will give us x is equal to 2 on 13 minus z. So now we have two equations which are as a function of z, and z is essentially a free variable. So what we're going to do is we're going to say z is equal to t, y is equal to 21 on 13 minus t, and x is equal to 2 on 13 minus t, because remember z has been replaced with t. This z became a t, this z became a t, this was our free parameter in this case. And now this is essentially the equation for the intersection of the planes, right? This is the line, and we can write this, we can rewrite these parametric equations in a vector form to give us x, y, z is equal to 2 on 13 and then 21 on 13 and then 0, and then plus we're going to have t times minus 1, minus 1, 1. And this is going to be one way to write the equation for the line, which is the intersection of these two planes. So in this case, the answer will be none of the above. Right? None of the answers listed are equivalent. All of those linear intersections are, all of those intersections there have a different slope value, they have a different starting value, so they are not the same. So none of those are correct, none of the above is correct, and so therefore E is correct.